And today we're going to talk about Taylor and McLaurin series. You may have heard of Taylor's and McLaurin expansion. And basically what we're doing in this section we are basically approximating a complicated function with a simpler function. And we do that by using, in calculus 1, there was something called linearization, where you kind of it was the same concept. You took a complicated function and you kind of reduced it to a simpler function. McLaurin and Taylor's expansion is basically the same concept. All right, I'm gonna bring up the set of notes and I'm going to share my desktop screen. All right, so in the lecture notes section, this is actually the section 10.8, and in section, and here again, there is an addition change. All right, but this is the Taylor and McLaurin series. And just to give a little background on this, we studied Taylor series because polynomial functions are easy to find if we can find a way of representing a complicated function as a series of infinite polynomials. And we can do this by what are called Taylor and McLaurin series. So in this section, we're going to show how functions that are infinitely differentiable. So what that means is you have a function and you can find its derivative infinitely, which means you can find the first derivative, second derivative, third derivative, so on and so forth. They generate power series that are called Taylor series. In many cases, these series can provide useful polynomials that can be used for approximating or useful polynomial approximations of generating functions. We also have something that's called a McLaurin series. The difference between a Taylor series and a McLaurin series is that a McLaurin series is centered at x equals to 0, where a McLaurin series is centered at x is equal to a. Okay. Now, when I say centered at, when you're given or when you're asked to find a Taylor or McLaurin series, you must be given two things. You must be given a function that's infinitely differentiable, and you must also be given a value in which your polynomial is centered. Okay, so the Taylor series is a function. It's an infinite sum of terms that are expressed in the terms of the function's derivative at a single point. So the single point is where your polynomial or your series would be centered. All right, so here's the formula. So we have the summation as k equals to 0 to infinity for the kth derivative. All right, so this f raised to the power of k is actually the derivative of a divided by k factorial is equal to x minus a raised to the power of k. Right, we can expand this out. Right, the summation is just a sum, or we're adding terms from 0 to infinity. So once we plug 0 into our function, we have f of a. Right, now 0 factorial, I'm going to bring up the calculator, okay, just to familiarize you with what a factorial is. All right, so here are just a couple of facts. Now, the way I can find factorial is I can go into math. I can scroll over to probability, and this fourth option is a factorial. So as a fact, 0 factorial should equal to 1. 1 factorial is also equal to 1. And I'll show how these things are derived in a second. 2 factorial that equals 2. All right, 3 factorial that equals to 6. So here's what's going on for 1 factorial. Okay, give me 1 second. I'm going to switch back to our okay, so just as a fact, 0 factorial equals to 1. 1 factorial equals to 1. 2 factorial. Now the factorials, we're basically taking the numbers in order. So I have 2 factorial, so that's 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, so that's where the 6 comes in. 4 factorial is 1 times 2 times 3 times 4, which will be 24, so on and so forth. All right, so if you're not familiar with factorials, this is how you can find a factorial analytically, or you can use a calculator. All right, so just keep in mind that 3 factorial is actually 6 and not 3. All right, so we have the expansion. We have f of a, right? So notice that 0 is substituted for k. So 0 factorial is 1. Here we have f raised to the 0 derivative. Keep in mind that this is a derivative, right, of a, and we have x minus a raised to the power of k. So here again, k is 0. A would be whatever your value is centered at, right? So this would give us f of a. On the next iteration, we would substitute in 1, right? So this is how this is expanded out. So we have f prime of a, right? So if k is 1, we're going to take our function. We're going to find the first derivative. We would substitute in a, right, which is what our value is centered at. 1 factorial is 1. Okay, here again, we would substitute a for the given value. K would be 1. And it would simplify to give us this second term in our Taylor's expansion, which is f prime of a times x minus a. And then on the next iteration, we will substitute in 2 for k, and so on and so forth. Here we have the McLaurin series, and keep in mind that the McLaurin series uses the Taylor series expansion. The only difference is that your McLaurin series is centered at 0, right? So wherever we see basically an A, we would substitute in 0. Okay. All right. Okay, now we're going to work with this formula just a little bit further before we actually take a look at some problems. You're going to be asked certain things like find the second order of a Taylor expansion, you'll be asked to find the first order or first degree. I wanted to explain what all of that entails. So I'm kind of write on horizontally because this is going to kind of go across the paper. So we have, this is the Taylor expansion. So we have the summation as k goes from 0 to infinity. For the kth derivative of a divided by k factorial times x minus a raised to the power of k. Right. So that's equal to f of a plus f prime of a times x minus a plus f double prime of a divided by 2 factorial times x minus a quantity square. Okay, I'm going to write out another term because I believe in the homeworks you may go up to this third degree. So plus f triple prime of a divided by 3 factorial times x minus a to the third power plus dot dot dot. Okay. All right. So now let me explain about the degrees or the orders, okay? Because you're going to be asked to find the Taylor's polynomial, the second order generated or the first order generated. So if you have an order of 0, that would only include your first term. If you have an order of 1, so this would be order 0. An order of 1 would actually contain the first 2 terms. If you're asked to write out a Taylor's polynomial of order 2, that would actually consist of your first 3 terms. 0, it would consist of order 0, order 1, and order 2. And then of order 3, it would consist of the first 4 terms and so on and so forth. All right, so keep in mind that order 0 or the Taylor's expansion of degree 0 is your first term. The Taylor's expansion of degree 1 would be your first 2 terms, so on and so forth. All right, so notice we would be given a function. We would be given a value for a. We would simply find the derivatives. We would evaluate the derivative at the value a. We would also evaluate our function at the value a. We would write out whatever order we needed, and we would substitute in those values. All right, so let's take a look at a problem. All right, now as far as the homework is concerned, I'm actually going to start with the second problem, and we'll kind of take a look at the second problem. We'll also take a look at this third problem. Okay. So here it says we're interested in the first few Taylor polynomials for the function 7e to the x plus 5e to the negative x. We're asked to find the first order Taylor's polynomial and find the second order or second degree Taylor polynomial. In order to do that, we need the following. We need f of 0, f prime of 0, f double prime of 0. Then we can write out our first order Taylor polynomial expansion. We can write out the second order or second degree, right, with these given values. Okay. So notice that this is also centered at 0, which actually makes this a Mclaren series. Okay. All right, so this is what I'm going to do. So I'm given a function, and I'm given a value for a. All right, so first I will use that Taylor's expansion, and I'm going to substitute. So I'm just going to write this out again. So this is the summation k equals to 0 to infinity for the k derivative of a, k factorial x minus a to the k. Okay. All right, so basically what I'm doing is I'm taking this, and the only thing I'm going to do here is I'm going to substitute a for 0, right? So if I substitute a for 0, I'm going to expand this out as f of 0 plus f prime of 0 times x minus a, right? So if a is 0, that's just going to simply be f prime of 0 times x plus f double prime of 0, because we're substituting a for 0, divided by 2 factorial, right, because that's a part of my formula, times x minus a quantity square. Well, if a is 0, this is simply going to be f double prime of 0 divided by 2 factorial times x squared. Okay. And this is where I'm actually going to stop my expansion, right? Because in the problem, we're asked for the polynomial of degree or order 1, so that would include the first 2 terms. We're also asked for the expansion of degree 2, which would contain the first 3 terms, right? So notice for my expansion, I'm using the 3 terms. So now I'm basically going to find all the elements to this. I have to find f of 0. I have to find f prime of 0. And I also have to find f double prime of 0. So if I hop back to the question for a second, this is the reason why they want you to find these following things: f of 0, f prime of 0, and f double prime of 0. All right, that reason is because they are needed for our expansion. All right. Right, so now I'm simply going to find the pieces to this puzzle. So we were given a function, right, and that function was, I'm going to slide this down here, f of x is equal to 7e to the x plus 5e to the negative x. All right, so we want to find f of 0. We have to find f prime of 0 and f double prime of 0. All right, well, we can find f of 0 by simply substituting in x for 0. So this is 7e to the 0 plus 5e to the 0. Remember that from the 0 exponent rule, anything to the 0 power is 1. So this is 7 plus 5, which is 12. Now I need to find f prime of 0. Notice that we were given f of x. So in order to find f prime of 0, first we must find f prime of x, and then we can substitute in 0. Okay. So I'm going to find my derivatives here. So f of x is 7e to the x plus 5e to the negative x. F prime of x is, well, when you take the derivative of e to the x, it returns e to the x. So we have 7e to the x plus, when you take the derivative for e to the negative x, remember that the derivative of e to the x, it returns e to the x, or it returns what you're given. In this case, it's e to the negative x times the derivative of your power. Right. So here I should have negative 5e to the negative x. So my first derivative should be 7e to the x minus 5e to the negative x. And for our second derivative, excuse me. So here again, the derivative for 7e to the x. So keep in mind, I'm pulling the 7 in front of the derivative operator. The derivative of e to the x is e to the x. So the derivative for that term is 7e to the x. And once again, I'm going to have a sign change. So I believe it should be plus 5e to the negative x. All right, so we have our first and second derivative. So now we must evaluate the first derivative for 0. So I'm simply going to substitute x for 0. All right, so this is 7 minus 5, which is 2. I'm going to substitute 0 for x in the second derivative. Okay, and it returns a 12. All right, so we have f of 0, we have f prime of 0, and we have f double prime of 0. All right, so now we're going to just expand this out by substituting. So we have f of 0, which is 12, plus f prime of 0, which is 2x, plus f double prime of 0, which is 12, divided by 2 factorial. So 12 divided by 2 factorial, which is 2, is 6x squared. All right. Okay, but remember now, this would, okay, I'm going to go back. So we have 12 plus 2x plus 6x squared. So if we were writing out order 1, I would include the first 2 terms. So t sub 1 of x that's equal to 12 plus 2x t2 of x. Okay, this is the second order, so it's going to include all 3 terms. 12 plus 2x plus 6x squared. All right. So here are our solutions. F of 0 is equal to 12. F prime of 0 is equal to 2. F double prime of 0 is 12. Here we have the Taylor's expansion of degree 1 and the Taylor's expansion of degree 2. All right, so I believe that was 12, 2, 12. Right, so that was problem number 2. All right. Okay, so notice we were given a function, we were given a value in which it was centered. Okay, we then found the first derivative, the second derivative. We evaluated each at what our polynomial is centered. All right, and then we kind of wrote out the degrees. Okay, now for problem number 3, we are asked to write out the Taylor's expansion, but we're given the information in a different fashion. We're given that g of 0 is negative 15. And I'm going to write this down as we go. G of 0 is negative. Okay, I don't think you guys are even seeing my screen. Okay, so this was Okay, what we just went through. All right, and this is problem number 3. So we're still asked to write out Taylor's expansion, right? But we're not necessarily given a function, and we're not necessarily given what it's centered at. I mean, this would be centered at 0. Okay, but they don't specifically write out what it's centered at. Okay. Well, it is right here. Excuse me. It says, what is the Taylor's polynomial for degree 2 centered at a equals 0 and degree of 3 centered at a equals 0? So let's write down all the given information. We have g of 0 is equal to negative 15. G prime of 0 is equal to 11. G double prime of 0 is equal to 1. And G triple prime of 0 is negative 18. Okay, so even though we're not actually given a function, we are given what it's centered at, but we're given the derivatives of the function. Okay, so we're kind of given the function in a roundabout way. We're also asked to find, without rounding, we're asked to approximate g of 0.1 using this degree 2 expansion, and we're also asked to approximate 0.1 using the 3rd degree expansion. All right. So I'm going to go back to the camera. All right, so this is what we have. G of 0 is 15. G prime of 0 is 11. G double prime of 0 is 1. G triple prime of 0 is negative 18. So if we take a look at our expansion, right? So instead of using F, they're using G, right? So in our expansion, we would have G of 0 okay, so I'm going to kind of write this out. So we have that's going to equal to G of 0 I think I'll write it out like this first in abstract form. That's going to equal to G of 0 plus G prime of 0 times X. So I want to show you where I'm getting this from. If we go back to our expansion, remember in the problem it told us that it's centered at 0. So if we were to stick in zeros for A, right, we would have F of 0, but in our case, G of 0 plus G prime of 0 times X minus 0, right, which is X, plus g double prime of 0 divided by 2 factorial times x squared plus g triple prime of 0, and I'm going to go down here. That's g triple prime of 0 divided by 3 factorial, right, times x cubed. So I kind of wrote that out in abstract terms before we start plugging this in. So keep in mind that even though they're using g of 0, all right, so we basically broke it down into g of 0 plus g prime of 0 times x plus g double prime of 0 divided by 2 factorial times x squared plus g triple prime of 0 divided by 3 factorial times x cubed. Now we're going to substitute in these values. Right? So I'm going to kind of do that right here. So we know the value for g of 0, right? That's equal to negative 15 plus g prime of 0, which is 11, x plus g double prime of 0, which is 1, divided by 2 factorial, which is 2, times x squared. So I'm going to write that out as x squared over 2 plus g triple prime of 0, which is negative 18, divided by 3 factorial, which is 6, times x cubed. So 18 divided by 6 is 3. So I believe that would be a negative 3x cubed. All right, so I'm going to just change that. So this is negative 15 plus 11x plus x squared over 2 minus 3x cubed. All right, so now I think we have everything that we need. We can write out, we were asked to write out, let's see, the second order. So T2 of x, that's going to equal to, so just remember from the second degree is actually going to be the first 3 terms. So T, the second order or second degree Taylor's polynomial expansion would be negative 15 plus 11x plus x squared over 2. The third order is the first 4 terms. Negative 15 plus 11x plus x squared over 2 minus 3x cubed. All right, so we're going to use these to approximate 0.1. So if we go back, okay, I'm trying to get back to the desktop screen. There it is. So now we're asked to approximate g of 0.1 for both the second and the third degree. So I'm simply going to take those functions and substitute x for 0.1. Now I actually do it here. I will use, I think I'll do it this way. I'm going to go into y equals, and for y sub 1, I'm going to put in that second order polynomial, negative 15 plus 11x plus x squared divided by 2. And for y sub 2, I'm going to put in that third order, negative 15 plus 11x plus x squared over 2 minus 3x to the third. Right. I'm going to go back to my home screen. I'm going to hit variables. I'm going to go over to y variables. I want the function. I want the first function evaluated at 0.1. I want the second function also evaluated at 0.1. Okay, there it is. It popped up. Cute. Let me check my function, make sure I put that in right. Okay, that should be a minus. I'm sorry, right here that should be a minus 3x squared. Just check what I have. Minus. Okay, that's a little bit. All right, so any questions about problem number 3? Okay, so just keep in mind when you're using the Taylor's or the McLaurin expansion, as you expand that out, your coefficients will have denominators, okay, 2 factorial, 3 factorial, so on and so forth. Okay, now just as a hint for the very first and the very last problem, you work them backwards, such as we did problem number 3. Okay, we kind of worked this backwards as far as what we were given. All right, I'm going to go back to the camera for just a second. I'll pull this up. I guess before I do that, are there any questions about the last section? Camera. All right, now as far as the rest of the semester, this is actually the last day of class. Our exam is on Wednesday of next week. Today, I'm in the process now of kind of finalizing some things as far as the final is concerned. There will be a final exam study guide. I'm not quite sure how I'm going to do that at this time. It may be some problems that already have the solutions that you can kind of just look through. The thing about this XYZ versus my math lab. For my math lab, when we were generating the problems, I had an algorithm and it would kind of change the numbers up on you. Most of the problems in this textbook don't operate the same way. You generally get the same problem over and over and over and doesn't change any values or anything. So I guess to avoid that, your review may be on like a separate sheet, or maybe on a, how can I put this? It may be on a written set of notes that I may just send out in a PDF, and it'll have the problem, and under the problem it'll have a solution. Okay, you can kind of work the problem, looking at the, work the problem, even though the solution is there, just to see if, you can come up with the correct solution. But the final exam is going to be Wednesday. You can take it before Wednesday, midnight. The time limit is set at 2 hours. Okay, I'm tentatively going to say it's set at 2 hours. I can't physically set it at 2 hours using the XYZ. I'm not quite sure if the analog representative can time it out or whatever, but keep in mind that there's a 2 hour time window on it. You can use a handheld calculator. You can use written notes. You can also use scratch paper and something to write with. Okay, but no cell phones, no iPads or anything to that effect. Right, so are there any questions up to this point? All right, so we won't actually meet again after today, but if you do have any questions, just feel free to send me an email. All right, so everyone have a good afternoon.